All right, what about the physical properties of ketones and aldehydes? So when we talk about physical properties of molecules, we are always trying to relate their structure to their intermolecular forces. And we know that that is determined by the types of intermolecular forces that they have. So the types of intermolecular forces include van der Waals forces, DDW. And they also include dipole-dipole forces. And then lastly, H bonding. And we've talked about this many times before. The lower on that list, the stronger the interaction. So hydrogen bonding is a stronger interaction than van der Waals, et cetera, et cetera. So the new thing here is ketones and aldehydes. We know that alcohols, carboxylic acids have 1 through 3, so all of the intermolecular force types. We know that something like pentane here only has van der Waals interactions. We would guess, you should guess, pause it for a second and guess what types of intermolecular forces ketones and aldehydes would have. Boop, boop, unpaused. They are going to have a dipole, right? Because oxygen is more electronegative than carbon, so they're going to have dipole-dipole forces and van der Waals forces. So these have 1 through 2. They do not have hydrogen bonding because there are no hydrogens attached to the oxygens directly. So these are going to have fewer intermolecular forces than these two, more intermolecular forces than pentane. So how does this relate to their physical properties? The boiling point of pentane is 36 degrees Celsius. This butanol is 118 degrees Celsius, and this propanoic acid is 141 degrees Celsius. So if we assume that the dipole-dipole interaction that these have is less powerful of an intermolecular force compared to the hydrogen bonding, we would assume that it's a higher boiling point than 36 and a lower boiling point than 118. It turns out that the boiling point of the aldehyde is 76 degrees Celsius, and the ketone is 80 degrees Celsius. There's not really a good way to say which one of these is going to be higher or lower. They're going to be pretty similar, so you definitely won't be asked those types of splitting hairs questions about, which one would you expect to be higher, the aldehyde or the ketone? But they have the same molecular weight, so they should have a relatively similar boiling point. If the ketone was double the size of the aldehyde, then it would have more van der Waals interactions, which should increase its boiling point. So that's something that we've known for a while. So that's kind of the background of these types of molecules. So we could separate them using distillation as a method or something like that. But now we're going to talk about how do we synthesize aldehydes and ketones. Because if we're going to do reactions of them, we need to be able to synthesize them. And these synthetic methods that we're going to talk through are all things that we've learned in chapters earlier in the book. So we already know how to take an alcohol to an aldehyde. You should take a minute to think about this and then unpause the video. And then also an ester to an aldehyde. We're able to do both of these reactions in a single step. With a single reagent. Take a minute, pause the video, see if you can see if you can remember, if you can rationalize what reagents we would be using here. Boop, boop. All right, unpaused. We have an alcohol. We oxidize that alcohol to the aldehyde. The oxidation reagents that we learned about are those chromium-based reagents. If we use the chromium 6+ reagents in the presence of water, we're going to go all the way to the carboxylic acid. We want to stop at the aldehyde. So that's the pyridinium chlorochromate reaction or reagent, and we use that in organic solvents such as dichloromethane. So that's how we go from an alcohol to an aldehyde. What happened here? Is this an oxidation or a reduction? This is a reduction. We have fewer bonds to oxygen here. So we had to have had some type of hydride source. Not sodium borohydride. That is not a strong enough reagent to react with esters. If we use lithium aluminum hydride, we're actually going to go all the way from the ester to the alcohol, so we need the Goldilocks reagent, the one that's just strong enough but not too strong. So that's that dibal H. So dibal H, and we can write low temp, and we'll write a solvent. So this was the diethyl ether or some type of inert solvent like that. The second thing that we have to add for this one is water, which is going to react with that aluminum reagent. So these are two ways that we can make aldehydes. Another way that we've learned to make aldehydes, and we'll just go up here, and I guess if we had to put these in context, this was chapter 20. We learned this just a chapter ago. The PCC was on the first exam, that's chapter 12, but we've been using that reaction in our synthesis problems from chapter 20, so it should be pretty fresh in our minds. What about another way to make aldehydes? This one's a little bit farther away, but there is a way to go from this alkyne and go all the way to that same aldehyde that we have here and here. And this is from chapter 11, so again, a little bit farther back, but this was the hydroboration oxidation. So the first thing that we use in this reaction is BH3. And then secondly, we work up in oxidative conditions. So we have some base, and we have hydrogen peroxide for our oxidant. This is chapter 12. So all of these, this is chapter 11. So all of these are ways that we can synthesize aldehydes. So go to the next page. So that was synthesis methods for aldehydes, but we also know of lots of ways to make ketones. So that was aldehydes. Now we're doing synthesis of ketones. And we're going to go from this alcohol and react it with something to make the ketone. And it turns out that, so what was this type of reaction? This is an oxidation. We're increasing our bonds to oxygen. Again, that's going to be chapter 12. And there are various ways to do that. One of the methods we already talked about with aldehydes also works for ketones is PCC and dichloromethane. And we don't have to say one here, this is just the only reagent here. We could use the Jones oxidation. So that's that chromium 6+ reagents. So if you want to remember that, go back to chapter 12. Maybe some of you, I'm sure a lot of you already remember it, but we'll just say Cr 6+ reagents, and then I'm going to write in parentheses Jones, because it's the Jones oxidation. So another way to make ketones there. What about if we wanted to make that ketone from this aldehyde here? So we are trying to make this ketone from that aldehyde. This is kind of like a miniature synthesis question right here. We're adding 2 carbons and somehow we're staying in the same oxidation state. This is going to be a 2-step reaction. In your notes, actually, it's 2 steps. And again, to orient you to the notes, this is page 3 of the notes. So we have to add a nucleophile to this carbonyl to add our 2 carbons on. What's going to do that? Any type of organometallic reagent, such as the Grignard reaction or organolithiates. So we could just have 2 carbons in our magnesium bromide in our inert solvent. That is going to produce the alkoxide of this. Secondly, we're going to have to add our proton source, so H3O+ is going to give a proton as an acid to this basic oxygen. And then the last step is going to be the same as above. We're just going to oxidize this with PCC. So we're going to write 3 here, PCC, and dichloromethane to make our product. So that is another way to make ketones. So that way, this first way is just an oxidation reaction. This way, we had to do multiple steps to actually add carbons to the molecule. What about if we had we wanted to make that same ketone, and I'm going to change it a little bit from the notes here. We're going to go with this 4-carbon unit instead of the internal alkyne. So this is a terminal alkyne. The way that we did this to make aldehydes is we took this and we did the hydroboration oxidation. And again, we saw back in chapter 11 that the hydroboration oxidation gave the aldehyde. If we want to make the ketone instead by an addition reaction, we use a hydration method. So we add sulfuric acid. I'm sure some of you remember the mercury reagent and water. So this reaction makes this alkyne react as a base. It will protonate from the sulfuric acid, and then water is going to add to the carbocation. It's going to add to the secondary carbocation because the secondary carbocation is more stable than a tertiary carbocation, and then we would have an enol, which would tautomerize over to the keto version. So again, this is chapter 11 if you want to go back and remind yourself of that. This reaction was chapter 20/12 because we did the oxidation after we did a Grignard addition to the aldehyde. So the last way that we know how to make something like this, it comes from the alkene. So if we had an alkene like this, pause the video for a second and think, oh, how could we change this molecule into that molecule? So whoop, unpaused. The way that we did this, and maybe I'll just give you a hint here, is we would split this bond right there, and that was through oxidative cleavage conditions, which was the ozonolysis, so O3. So everywhere that had an alkene, if you treat that with O3, it's going to cleave all of the alkenes and put oxygens on either side. So this is a CH2 here, so this ozonolysis, and then you have to reduce it afterwards with something like dimethyl sulfide. So that ozonolysis cleaved that alkene, made this, and it also makes the other carbon of the alkene. So this carbon also has a new carbonyl bond. So that's pretty much all the ways that we know to make aldehydes and ketones. Hopefully that's a good introduction to remembering all of those methods that we learned, because technically all of this is review. So hopefully this seemed like, oh man, why is he even putting in this chapter? It's all review. It is all review. So hopefully that makes sense, and we will get more into chapter 20 next class. So I will see you guys at that point. All right, bye.